2.5, day 10. Talking about inverse and composite functions in this section. But these notes today, we're just going to focus solely on the inverse functions. So let's jump in with some inverses. First example, this is a short, quick one here. Let's make a little table with x and f of x. So the x's, they just go from -1 to 3 by ones. F of x, they start at 2, go up to 10, count by 2's. So when we talk about the inverse of a function, we did this in Algebra 2 also. It's pretty much we switch the x and the y's. So if this is x and f of x, for f inverse, for the inverse, it's exactly what you would expect. The f of x values go up top, and the x values will go down below. So notice how they just switch. So now instead of x f of x, we have x versus f inverse of x. That's the notation. It's that little -1 in the exponent. That means inverse. So in general, inverse operations mean they will basically undo each other. So for now, what do we just show? The x and y values will switch, which also implies what? If the x and y values can switch, graphically that means the domain and range will switch between these two graphs. So if the x and y's are just switched, the domain and range will just switch. And notice in pre-calc a lot of times we don't say x, y, we say x, f of x. We use that notation. But f of x and y are interchangeable. Okay, so inverse functions algebraically. We just looked at a table and found a function and its inverse. But now we're going to have to find them algebraically. And this is also something we did in Algebra 2. So I'll give you a function for example 2. Part A says find f inverse of x. That's how you read that. Find f inverse of x. So I got to give you the function first before you can find the inverse of it. So here's the function here in purple. F of x equals 2x minus 1. Okay, so what it comes down to is we're going to undo all these operations on x. And if you remember, the first thing we do is we're going to rewrite, to make things a little bit easier, we're going to rewrite f of x as y. So instead of having this f of x in here, we'll just call this y. So that'll be our first step, is just call this y equals 2x minus 1. When we start doing the algebra, it just becomes a bit easier. So y equals 2x minus 1. Okay, and the next step is we're going to switch the x and the y. So we just showed that the x and y switch with a table. So we're going to do the same thing here when we solve it algebraically. So let's switch the x and the y. That's step 2. So we're going to find the inverse of this function. Step 2 is switch the x's and the y's. So where you saw a y before, now you see an x. And where you saw an x before, now you see a y. So we just switched them. And then the last step is just solve it for y. So solve for y. So that should be pretty simple. Add 1 to both sides. Divide by 2. So we got y equals x plus 1 over 2. And that actually makes a line. Let's write that in slope-intercept form. So since it's x plus 1, the whole quantity over 2, we can split that up and just call that 1/2 x plus 1/2. So now you know the y-intercept's 1/2 and the slope's 1/2. Okay, and then the last step is rewrite this line. I want you to return to function notation. What do I mean by that? Return to function notation. Okay, so first step we did, we switched it to y equals. So the question asks to find f inverse of x. So I just want you to switch it back to function notation. And now that we're done, we're going to rewrite that y part as f inverse of x. So now our last step here is just say f inverse of x equals this thing, 1/2 x plus 1/2. So those are your steps. If you want to solve and come up with the inverse of a function algebraically, it's the same steps no matter what the function looks like. Put the y in there to make things easy, switch the x and the y, solve it for y, and then when you get done, don't forget to return it back to function notation. Put the little inverse symbol up here. Okay, so part B, let's look at the graph of those two functions, f of x and f inverse of x. The same ones we just used, so I'll bring that up on my screen here again. So f of x was 2x minus 1, and then f inverse of x, we found that to be, I'll do that one in green, f inverse of x is 1/2 x plus 1/2. They're both lines, but let's take a look at the graph. You may already remember this special relationship between inverses. But I'm going to make this graph, and I'm going to be kind of precise about where I put the points here. So I just mark my axes out to 5 in each direction. It should be pretty simple to graph too. The 2x minus 1, the y-intercept's -1, the slope's 2, so put some points down, and again I'm going to try to line things up really nicely so we can see this result when we get done. So in purple here, here's my line for f of x. Y-intercept's -1. Slope of 2. And then in green, let's go ahead and graph this line. So the y-intercept's 1/2 and the slope's 1/2, so that's up 1 over 2. And put those points down. I tried to get it as exact as I could. So in green here, this is f inverse of x. Okay, so if you drew this nicely on your paper, you'll notice it has some sort of symmetry, right? The lines kind of cross nice, but there's some sort of symmetry there. I'm going to go ahead and start by drawing in that line of symmetry. It's this line right here. So all these functions and their inverses, they all have symmetry with this line. What is that line? It's diagonal. Well, that's actually the line y equals x. So the line y equals x, that's got a y-intercept of 0 and a slope of 1. So it is a perfect diagonal that cuts through here. So what can we say? Inverse graphs, I know these are just line, but any inverse graph, they're going to be symmetric about the line y equals x. When we talk about symmetric, we mean they're really just mirror images of each other, just reflected over that line y equals x. Which should make sense. Algebraically, we just switch the y and the x. They're interchangeable. So now graphically, it flips over that line y equals x. So just as a refresher, don't forget the x's and y's switch when we're finding these inverses. So it should make sense that the graphs are actually a reflection over that line y equals x. Example 3. So given a function, f of x, it's equal to x over the quantity x plus 1. Find f inverse. So that's another way to write like f inverse of x or the inverse function. You just have an f with a little -1 on top. So that's another common way you'll see it. So find f inverse. And again, we're going to do this algebraically, so it's the same exact steps we just took. So let's simplify things. Instead of having this as f of x, let's start out by just calling that y equals x over x plus 1. Then you probably know what I'm going to say. Go ahead and switch the x's and y's. So where you see a y, you better put an x. Where you see an x, you better put a y. So let's switch those around. So now I got x equals y over y plus 1. And now here comes the fun part. You got to solve it for y. It gets a little weird because we have a y in the numerator and a quantity y plus 1 in the denominator. No, those y's do not cancel. That is not a thing. You cannot cancel these y's. Don't even think about it. That's not a thing. So how do you go forward from here? Well, we really want to get this y plus 1 out of the denominator. So that's really our goal at this point. So we're going to solve for y by getting that y out of the denominator. So to do that, we could just multiply both sides by y plus 1. If we multiply both sides by y plus 1, it would cancel out over here on the right side, and it would pop up here over here on the left side. So that's the way you can clear out a denominator when you see something like this. And there will be more problems like this. Kids always kind of get stuck on these, so let's make sure we get it good now. So if I multiply both sides by y plus 1, how's that going to look? Y plus 1 over here, y plus 1 over here. The whole reason I do that is so I can get it out of the denominator, and then it shows up on the other side. So now these y plus 1 terms cancel. I got y plus 1 x equals y. So now I got the y out of the denominator, but it still looks a bit messy. I got a y over here, I got this y plus 1 quantity over here. So the best thing we can do right now is start to simplify a little bit. Let's distribute this x through this quantity. And then let's see if we can get the y's together all on one side. So let's take a look. So right now, if we can just go ahead and distribute that x through there. Distribute the x through. So I got xy plus x. Don't forget to multiply the x by that 1. xy plus x on the left-hand side, and the right-hand side didn't change. I still have a y. So now this is good. I have one y over here, and I have an xy over here. We can treat this like any old equation. Let's get the y's to one side. Let's get everything else to the other side. So that's our objective at this point. So let's get all the y terms alone on one side. And we can do that in one step right here. Hopefully you see it. Just take a look at that xy. If we subtract xy on both sides, we'll get to where we need to go. So subtract that xy on both sides. I'll just have x left over here. So I got x equals y minus xy. Okay, so far the algebra probably followed pretty nicely for you. But here's the part that really throws kids for a loop. Okay, I have a y and an xy, but I really just want to solve for y. Like I want to have y equals a number when I'm done. So how do I get that y by itself, essentially? How can I solve for it? Here's the trick. That's a y, and there's a y in this term. So between these two terms, they both share a y. Big hint, you need to go ahead and factor the y out of this. So if you can factor a y out of these two terms here, then we'll have something we can work with. So if I factor, that's the big secret here. That's the big take home. Factor out a y. So how's that look? X equals, and now I just factor out the y, I have y times 1 minus x. In this point, we're pretty much home free. Look, we got one single y in there. Y times this quantity. So now if we can just divide by 1 minus x on both sides, we'll be in business. So that's the last little bit here, is just solve this by dividing by 1 minus x. And we'll have y all alone. So those 1 minus x terms will cancel out on the right-hand side. What do you know? It showed up on the left-hand side in the denominator. It's okay. So y equals x over 1 minus x. This is really great, and it's all grand, but we were really looking for f inverse. So last step, don't forget it. Let's go ahead and return this function back to inverse notation and call it f inverse of x equals that x over 1 minus x piece. So again, this is the same exact steps we took on the previous problem where we solved for algebraically. Big takeaways. You have y over y plus 1. Multiply both sides by y plus 1 to clear out that denominator. Distribute that x through. Get all those y terms together on one side. Once you do that, you can factor out a y and divide by the leftovers. And then we get our solution for f inverse. All right, example 4. We're going to find the inverse function for what? Find the inverse function. What am I going to give you? I give you f of x equals 2x cubed minus 4. So that's the function. What's that function's inverse? So essentially we're going to undo all these operations, and we're going to do it algebraically like we've done 2 times already. So first thing, let's replace that f of x with a y. Then pull the old switcheroo, as I like to call it. Switch those x and y's. So now I got x equals 2y cubed minus 4. And let's go ahead and solve for y. It's only a few moves. But let's take care of the easy ones first. Let's clean up this equation a little bit. Add 4, that'd be the first order business. Add 4 to both sides. So x plus 4 equals 2y cubed. Then divide by 2, and then we'll take care of that cube. We'll take care of that exponent last. So divide by 2. So I got x plus 4 over 2 equals y cubed. Now let's go ahead and cube root both sides. That's how you get rid of a power of 3, that exponent. You cube root both sides. And you don't have to worry about putting plus minus. That's only for even roots. Square roots or fourth roots. So cube root both sides. Now I just have y equals the cube root of x plus 4 over 2. And last but not least, we're going to finish this thing up, put it back in a function notation. This is f inverse of x equals cube root of x plus 4 divided by 2. So same exact steps, did it algebraically. That was the 3rd time. Okay, little bonus question. I want you to evaluate f inverse of 12. So we're really used to seeing like f of 12. We're not really used to seeing f inverse of 12. But look, we have the inverse function right here. So function notation means to plug something in. So f inverse of 12, here's f inverse of x. We just have to go plug 12 into this function and get our answer. So that's pretty easy to do. It's the cube root of x plus 4 divided by 2. Notice I left the x blank because I'm going to plug this into the inverse function. Just put the 12 in there. These numbers actually simplify all the way down to a single whole number because this is the cube root of 16 over 2. Let's take care of the easy stuff on the inside. 16 over 2, that's a good one. So cube root of 8, which is actually a very special number, otherwise known as 2. So that's how we can evaluate values in the inverse function. Once we have it, if you want me to plug this in for x, I plug it in for x. Don't plug it back in here though, that's f of x. If it says f inverse of 12, make sure you plug it into the inverse. Okay, then part B from that example. Let's do one without some x and y's. So I got c equals 2 pi r. Hopefully you recognize that. That's the circumference of a circle, 2 pi r. So the circumference is a function of the radius. I want you to find its inverse. So the first order of business would be to switch the variables, c and r, and solve for c. So just divide both sides by 2 pi. And then what do we have for c? So I get c equals r over 2 pi. And since this is the inverse function, let's go ahead and put inverse notation on it. I know it wasn't in function notation up here, but since we know already to start out that circumference is a function of the radius, let's go ahead and call this c inverse of r is r over 2 pi. So same steps, switch the variables, solve for the one you switched, and then write it in inverse function notation. Okay, that's the last one we're going to do like that algebraically. One little bit left. So example 4. I'm going to start out with just a couple axes, and I'm not marking them off or anything, but just as a general estimate, I got 8 on the y-axis marked off and 4 on the x-axis. I didn't use tick marks, I just put it down as just an estimate. Okay, and now I'm going to sketch this graph. I got a closed circle at 8, and it goes through 4. That's why I drew them. That's why I drew 8 and 4. And this purple graph here, that's going to be my f of x. So this is where I'm going to start you out. And I want to know what's f of 4. So I don't have any funny business going on right now. This is literally just a graph f of x. I want to know what's f of 4, which means what happens when you plug an x value of 4 in. 4 is right here on the x-axis. So for an x value of 4, the y output would be 0. Okay? So how about f of 0? So when you plug in 0 for the x, what's the y? What's the output, the height? Well, that would be 8. So those are no big deal. We've done a bunch of those. So now, just based on this graph, I want to ask you, what would f inverse of 0 be? So now you really have to think backwards. Since f of 0 meant when you plug in 0 for x, you get an 8 out for y, this really means the opposite. When you plug a 0 in for y, what do you get out for x? So that's what the inverse does, right? It flips things, means the opposite. So let's think. When I'm at a 0 for y, what do I get out for x? So my y coordinate, when that's at 0, my height's at 0, my x is actually 4. So notice the relationship here. F of 4 was 0. F inverse of 0 is 4. So now it was like we were looking for the y value to get the x out. Let's try another one. F inverse of 8. So I'm not looking for an x value of 8. I want to know for the y value of 8, what's the x value? Well, when we're a height of 8, right, that point, the coordinates are 0, 8. So the x value for a height of 8 would just be 0. So this is a little bit of a new concept for us, just using the graph of f of x, and we found values for f inverse. And notice the relationship. F of 0 equals 8. F inverse of 8 would be 0. So we're going to take a look at this f of x function from a couple different directions. Let's throw the values in a table. So for x, we know one of the coordinates was 0, 8, so when x is 0, f of x is 8, and the other one was 4, 0, so when x is 4, f of x is 0. So let's use that same logic to make the table for f inverse of x. So x versus f inverse of x. We just put the f of x values on top, so they're switched, and now 0, 4 will go on the bottom. So this is the exact same concept as these values up here. F inverse of 0 is like plugging 0 into this function, your output is 4. F inverse of 8, plugging 8 into this function, your output is 0. And all we did was just make two simple little tables with the x's and y's switched. Okay. How about the domain of f inverse and the range of f inverse? I know that seems like maybe a difficult question, but it's actually pretty simple. So if you know that the domain and range switch for inverse functions, to find the domain of f inverse, all you would have to do is tell me the range of f of x. So what is the range of f of x here? Well, looks like the highest it ever goes is 8, and it's got this arrow trending off down towards negative infinity. So negative infinity to 8 would be the domain of f inverse. How do I know that? Because that is what we just said to be the range of f of x. So they're interchangeable. Okay, then what would the range of f inverse be? And don't worry, we'll graph this in just a second. What would the range of f inverse be? Well, the range of the inverse would be the domain of the original function. So what's the domain of f of x here? Well, it looks like for the x values, 0 to, and this arrow is pointing off to the right, so that's going to trend towards positive infinity. So for the x values, the domain of f of x would be 0 to infinity, which means the range of f inverse is 0 to infinity, because that's the domain of f of x. This is what we started the lesson with. The range of f of x, that's the domain of f inverse. They just switch. Okay, so then we could easily graph f inverse. I mean, we've already got the table here. So let's plot the point 8, 0 and 0, 4. We'll do that one in green. There's f inverse of x. And if your sketch is any good, hopefully you'll see some symmetry here. You'll see this reflexive property. And I'm even going to sketch the line y equals x right through there because I know that's what these two functions reflect over. So we created essentially every single piece of this, evaluating two tables, domain and range for both functions. We created all that just by this one little piece of a graph. Okay, that's all for these notes. I'll see you in class tomorrow.